All right, here we go. This is lesson 9D in your binder. So we're going to talk about correlation and causation, and sometimes how these are confused. So you read in the preview assignment that little article about SIDS and some of the incorrect conclusions that were drawn here. So this is one of the big pieces here. Correlation does not always indicate causation. So they ask you right off the bat, can you think of a couple of things that seem to be connected, right? So they're related, but one of them doesn't cause the other one. So there's kind of a classic example. You can Google it, right? So there's this one here that has to do with ice cream sales. I like this example. And then also, you might be surprised, murder, right? Or you could just say violent crime. So this is kind of interesting because there's been a lot of data collected on this idea that as this variable increases, right? So as we sell more and more ice cream, there's more and more violent crime. So this is kind of neat because when you think about the two, they're connected, right? There's a correlation, but that doesn't mean that one of them causes the other. So we're not saying that ice cream sales, right, cause violent crime. So this is a good example of where two things can actually happen together, but that doesn't mean one causes the other, right? So you could probably Google some other examples of this and find some other examples that you can add to that. All right, so this is probably the main thing we're going to do, and also we'll look at a scatter plot. I'll provide another screencast showing you how to do that. So let's look at question 2 here. It's saying let's look at the following statements, and if you think one causes the other, or maybe there's just a correlation and not causation. So we'll look at these different examples here. All right, so here they are. Problem A, right? Every time I eat chocolate, it makes my face break out. So this is kind of a neat one because this could be true, right? This could be a causal connection. So it could be an ingredient in the chocolate. So I'll say maybe on this one. But the other things we have to sort of think about is it could be something like stress, for example, right? So you might be stressed out, and then every time you get stressed out, that might cause your face to break out, and at the same time, that might make you eat chocolate, right? So there could be something extra there that's kind of connecting those two. But I still think this could be a possibility. How about B? It says, recent studies have proven that watching too much violence on TV sort of makes people violent in real life. This one here, I'm going to probably say no, because I've seen data on this. So this one, probably not. Mainly this has a lot to do with societal changes and the economy. So lots of data has indicated that if we have a stable economy, it doesn't really matter what you're watching, violence is going to drop. So that one, probably not. And let's read this one. This one's kind of silly. Baseball player tells his friends he didn't change his socks for 3 games, and the team won all 3 games. So the player concluded that wearing those socks, right, caused the wins, right? And of course, what he's going to say is, hey, for that next game, I'm not going to wear my socks again. So this is all I have to say for that one, right? So it's probably purely a coincidence, right? So the two events did occur together, but that definitely doesn't mean that the smelly socks led to the victory in the games. So that's a good example to refute that. All right. So hopefully that stuff makes sense. I like these graphics here that they show you at the end, because we'll see a scatter plot that sort of talks a little bit about this. So to understand these, what we're really doing is we're thinking about these on a set of axes, right? Where x is your independent variable and y is your dependent variable. And so if you just look at the one where I drew the axes, this is showing that as x gets larger, right, the same thing is happening with the y's, right? So y is also increasing. So we say there is a positive correlation, right? There are some exceptions to the rule here. Like this has a pretty small x, right? But it has a pretty large y, and that's why they use the word weak, right? So it's not a very strong correlation. So examples where it's pretty strong is where when you look at the dots, it almost looks like a straight line, right? So the pattern is so strong. And in this lesson, we'll see an example of this one, right? Where as the x gets bigger, what happens is the y's are dropping, right? They get smaller. So these are just some nice pictures so that we can internalize what this looks like. Right, on to page 3 here. So this is where we really start to talk about some of the mathematics here. So question number 3, it's saying, okay, these variables are correlated. Are they positive, negative, or 0, right, the correlation. So problem A is talking about CO2 levels, right? Since the 1950s, these have done pretty much nothing but that, right? They have gone up. How about obesity levels? Well, they've gone up too, right? So this would be an example of a positive correlation. So notice we're not saying causation. We're not saying that high CO2 causes obesity, and we're not saying it the other way around either. But in here, we're just trying to identify a connection, right? A relationship between them. So let's look at B. The height of school-aged children measured in inches, and then the exact same variable measured in centimeters. So this here is going to be an exact, super strong positive correlation, and that's because we're pretty much measuring the same thing, right? The same variable, but we're using different units here. So you could use this, you probably don't need it. 1 inch is about equal to 2.5. So 2.54 centimeters. So because there's a way to convert from this to this, that means your correlation is going to be perfect, right? So that one's going to be positive correlation. How about problem C? The age of the model of a car. So as time goes by, the age is going to go up. What's going to happen to the value of the car? Well, that's the opposite. It's going to drop, right? So we saw that in a different lesson. And this will be pretty strong as well, right? The older your car is, the less value. So this is going to have a negative correlation. Okay, one variable goes up, the other goes down. So that's pretty nice. All right, so let's look at problem 4. This one actually kind of reminds me of the ice cream problem that I gave earlier. So it's saying here we're hanging out at the ocean, eating an ice cream cone. And a student says to his teacher, wow, you better be careful when you eat that ice cream because there's a high correlation between eating ice cream and drowning, right? And that's probably true. So the teacher's confused because the student says, hey, don't you know that days with the most ice cream sales also have the most drownings, right? So then they ask you this question, right? They throw in that word, cause. And the answer here is no. So eating ice cream doesn't cause drowning. This is an example of what we would say there's a lurking variable in here. Right? So we can definitely say they're correlated. But I think the lurking variable here is the day of the year, right? The day of the year, or you could say the season. So when it's very, very warm, you're going to eat a lot of ice cream, and the warmer it is, the more you're going to swim. So then it seems to make sense that you're going to have more drownings if you have more people in the water. So that's really talking about basically 3 things, right? Consuming ice cream, what the weather is, and also drowning. So if you pull one of those variables out from the picture, then it appears that one of them is really closely connected to the other. So that's definitely a no. Okay, so hopefully that is all good. And now we'll finish with our last problem, but this one is pretty long. They have a lot of information here in number 5. And so what we're going to do is to look at how heavy cars are, right? The weight of cars, and then also their gas mileage, right? The efficiency. So mpg is miles per gallon. So you can look at this data and you can definitely see some trends. I do like that when they did this, notice they didn't put these numbers in order, right? So the biggest one here is right here, that 4,915 pounds, and then the miles per gallon, 18 mpg, right? So they didn't put them in sequence. So let's go through and look at that. So I'll pull this data aside because I might need that a little bit later. And then we're going to do some work here on this. So pull this here. So the first thing here they ask you to do is to create a scatter plot. So just like I showed you in the screencast, you can do that in Excel, so you can generate that. So I printed it out here. It looks something like this. And this again sort of makes sense with what we've already seen because this is definitely a negative correlation. So as the weight of the car increases, right? So heavier cars, you can see the basic trend is this. Fuel efficiency goes down, right? So here's a car that's very heavy. It's not very fuel efficient. Up here is a car that's very, very light, right? Doesn't weigh much at all, but it's very, very efficient. And that trend you can sort of see, right? And that's indicative of a line that's falling from left to right. So that's really what the scatter plot looks like. So I'll hold that. We might come back to it. So part B, does there appear to be a correlation in the data? This one here we would say definitely, right? So strong, probably say strong negative correlation. Right, so I already mentioned that on the last frame. That's because as the weight goes up, the fuel efficiency drops, right? So you're seeing that kind of that change in the variables. Okay, look at part C. What are some other things that could be impacting this, right, besides weight? So they're talking about what are some of the lurking variables. So I think here it might be the style of the car, right, the make, one of those things. Because some of the sports cars, right, for example, are meant to be more aerodynamic. So because of that, they might have less drag and they might have better MPG, right? So there are other things. It's not just how much the car weighs, but I'm guessing that the weight of the car is probably the most influential. All right, so part D, probably need a piece of paper to do this, right? So I'm going to grab a piece of paper here. So it's saying pick any two ordered pairs from the table and find the equation of the line that passes through those 2 points. So let me do some math here. So I'm going to do this. I'll grab some paper. So I'm going to grab the points that are on the ends. They'll probably be most accurate if we do that. So this is the lightest car here, and this is the heaviest. Okay, so if you want to compute the slope here, so we saw this again in an earlier lesson, that's the change in y over the change in x. Right, so this is the kind of math we're going to do. So you can subtract the y coordinates here. So this will be 29 minus 18. And then downstairs, you subtract the x's, but in the same sequence, right? So we started with 29, so we start with 3,085 minus this result here, 4,915. So we do that kind of math. You can jump on a calculator to do this work. That's totally fine. And then we can estimate. So this is what I'm getting here. Really, really small negative number, right? So that's what we get for the slope. Right? Now really you could do that with any two numbers on this table. You're going to get something pretty close to this, but it could be different mainly because if you're using two different points, you're doing a slightly, this here doesn't represent a perfectly straight line. So that's just a matter of choice. So coming back to this, when we look at this, find the equation of the line, there's still more work to do. So there's a lot of math in this particular one. So again, this is going back to an earlier thing that we did in the class, right? This is the equation of a line, right? Y equals mx plus b. What we just found right here is m, okay? And now to finish this, I'm going to come back to the table. So I'll come back here, right? So I'm going to just pick one value for x and one value for y. Let me just grab this one. Right, so I'm grabbing this right here from this table, 4,915 and 18. So what I'm doing is I'm picking that for my x and picking this for my y. Put that aside. So you have to do a little math here. So the m we can put right in there. The x will be the 4,915, and then the y will go right here. And what that will do is it will leave you with b, so then you can solve for b. So you do have to do some mathematics here. So I'm going to write this down. This is going to be y equals mx plus b. So I hope that makes sense, right? This is your y, that's your m, that's your x, and your b is unknown. So the rest of this, I'll let you check this out on a calculator. You want to multiply these two and get this number. Whatever you get here, you get around, I believe, negative 29. You have to add that number to both sides, and then you can solve for b. So what I got here, got this for b, right? So 47.49 or so. And then you're all set, right? So you have the equation of the line because m is right here and b is there, and you're done. So let's write that down. And that should finish this one. So y equals mx plus b. Okay, so these we had to find from scratch, right? So I just showed you the details of that. So that would answer part D, right? So that's the equation that you can use. All right, so hopefully that's good. Just a couple more parts here, and this one will basically be done. So let's do part E, right? So use the equation to find the miles per gallon for a car that weighs that much, right? So about 2,200 pounds. And so the idea is that, remember, if you look back at our table, the pounds, right, was the x, and then the miles per gallon was the y. So what part E is really asking you to do is to use this for x, right, and then to calculate the y. So I'm going to do that here. So this is a direct substitution, right? You're letting x equal 2,269. And again, just do the calculation. So you multiply these together and then add on the 47.49. You end up with pretty close to 34. This is what I got on a calculator. So I'm just going to round it here. About 34 mpg, miles per gallon, right? So that's how you do that. They do ask you a question. Is this interpolation or extrapolation? So interpolation, right, is when you're kind of doing some calculation within the data. Extrapolation is outside of the data, right? So this could be data that's smaller than the data that you have or data that's larger. So if you look at the table, see if I can get both of these in here, right? Our input variable for this one was 2,269, and if you look up here for the weights, we have nothing even close to 2,269. So this is an example of extrapolation because it's outside of our range. If we had a number sort of like 3,600 pounds, that would be an example of interpolation because that falls within the range of the numbers that we see here. So this one here, definitely extrapolation. Okay, Good deal. Okay, last couple of things here. Part F tells you go to this website. I visited, I think, a different one, but it has the same basic information. So it's all about the 2011 Mazda 2, right? So I looked up the information. Google will give you anything, right? And this is what I found. Pretty efficient car, right? Remember, this is a highway miles, right? So 35 miles per gallon. And it tells you compare your answer. So this data here corresponds to what they gave you in this problem, right? The 2269. So if I pull this over here, I mean, that's pretty darn good, right? So you can see the model that we built up here makes this sort of as a prediction, and you can tell that's pretty close to the reality. All right, so last two parts here. They're asking you interpret the slope and also the y-intercept. And so we'll have to come back to the model here. So maybe I can write this here so I have some space. Right, so interpret these in context. So these maybe I'll just talk about. So the y-intercept is this thing here. So what that's really telling you is if x is equal to 0, right, if you just let x equal 0, this is what you would get for miles per gallon. So this one here is pretty weak on interpretation because you can't have a vehicle that has no weight, right? So this part of the interpretation doesn't mean a whole lot, right? So it's just telling you if you didn't have a car, that would be your fuel efficiency. That happens sometimes in mathematics where your models will break down because sometimes the interpretation isn't realistic. The other one, on the other hand, is. So it says interpret the slope, right? Like, what does that mean? So the slope in this problem is that very small negative number, right? So it was this number here that we calculated. So what this is telling you is for every single pound of weight, right, your gas mileage is going to drop by 0.006 miles per gallon, right? So that's the interpretation here. You can tell there as x increases, right, as you put bigger and bigger numbers here, this number is scaling that number, right? So every pound of weight that you add on, the gas mileage drops precisely by that many miles per gallon. All right, and the last question, part H, is saying talk about B and G. So I think it's enough there to say if you look back at the information that you look at this graph and this here has a fairly strong negative correlation because increase in this variable, decrease in that one. So that strong negative correlation can be seen in the negative slope, right? So that's the reason you end up with a negative number here, because one number is increasing and the other one is dropping. All right, all done.